Okay, here we're going to look at uh, deriving a formula for impact velocity of something that falls a certain distance. And if that's all you know, that how far it falls, you should be able to figure out its distance. And we're going to be able to do this through the process of a conservation of energy. And so before we look at this, we'll have like a cliff here that we're going to fall down. We'll say it's like 80 meters. And I want to know with what impact velocities are going to hit the ground down here. So a couple things we need to look at here is the two types of energy. We have potential energy, which is actually called energy of position, and it's based on the mass of the object, the gravitational constant of the planet, and the height that this object is at the current time and how far it's going to end up falling. So this is potential energy, and the units for this is joules, as we showed in the derived units video, joules. And then there's another kind of energy, kinetic energy, which equals 1/2 mv squared. And this is also joules. And this is energy of motion. You'll notice that kinetic energy it has a velocity in there, so it's talking about how fast the object is going. And there's usually kind of a interplay between these two. One is always converted kind of into the other. So if you have like a classic example is a pendulum, you take a pendulum and you drop it and it swings down around and it comes up to the other side. Right here at this position, it has all potential energy. But as it starts to swing down, you'll notice that the lowest point it's going to get is to here. So there's an actual height that it's falling, and as so it has all of potential energy right here, and no kinetic because it's not even moving. But then I let it go, and it starts to move faster and faster and faster, which means the velocity goes up, which means the kinetic energy of this pendulum must be going up. But you'll notice the ball is getting closer and closer to the lowest point, so it's losing height. So the potential energy would be going down because it's losing height. Kinetic energy would be going up because it's gaining velocity, and that's equal to each other. So whatever an energy that this object loses in potential, it gains in kinetic, which means at any point on this entire path, if you add them up, potential and the kinetic at that location, you'll get total energy, and it will always remain constant. And that's not technically true because we have air resistance and friction and things that can work against us, but in a perfect world where there was no air resistance or anything, this would just keep going back and forth forever. It would never go higher than where it originally started from, but it would make it back up to its original height. Normally on the Earth, this pendulum is not going to actually even make it up to its original height because of air resistance and things. But at any point on here, if I have the pendulum at this point right here, there's still some height, so it still has some potential energy we can calculate. And now it has a little more velocity, so there's kinetic energy we can calculate. And if we added it up, we get total energy. We get the same amount of total energy that we would have right here at the beginning. Now at this point, your total energy would be mgh, potential, and there would actually be no kinetic energy. The velocity would be zero. So the potential energy right here is the same as your total energy right here, because here your kinetic energy is zero. And so when the pendulum gets down here on the very bottom, ooh, that's really, really bad. Should go straight down. When the pendulum gets down here to the bottom, it'll be down at the bottom of the height. So for height, we'd put zero. So here it has no potential, and it's going as fast as it possibly can. So it would be all kinetic at the bottom. So at the top, it's all potential. At the bottom, it's all kinetic. And then it goes back up the top where it's all potential again and zero kinetic. But if I always add up potential and kinetic at any point on this path, they will give me a total energy. So that's kind of important here to help us figure out our derivation, because we're going to have an object here that's going to fall all the way down 80 meters. It's going to fall all the way down to the ground here, and it will fall in a straight line, not a curved line like I just made. And so at the top, it has a certain amount of total energy. And at any place down here on the fall, I can take different places down here in the fall, it'll still have exactly the same amount of total energy the whole way. Even right here as it's about ready to hit, it'll have the same amount of total energy. And the equation for the total energy is potential, mgh, plus 1/2 mv squared, the kinetic energy. So that would be the same all the way from the top to the bottom. So what we can do is, if we know that the total energy at the top equals the total energy at the bottom, we can use that to start our equation, because we're trying to derive an equation for the velocity of this object down here at the bottom when it impacts the ground. And apparently it's only based on whatever the height is of this whole thing. So we can do a conservation of energy equation here to do this derivation. So we're going to have total energy at the top should equal total energy at the bottom. Well, the total energy at the top is going to be mgh. We'll call it h1. So up here at the top we'll call this h1, and then down here at the bottom we'll call this h2. And up at the top we'll call this v1, the velocity of it is v1, and down here we'll call it v2. So we have mgh1 plus 1/2 mv1 squared is the total energy at the top. That will equal the total energy at the bottom, which is mgh2 plus 1/2 mv2 squared. So these have to be equal. Now, some of these things we know that at the top it's all potential and there is no kinetic because the velocity is 0. So right here for v1 we'd put a 0, and that actual term would not exist in the equation. Likewise, down at the bottom we have a lot of velocity, but we have no more height left. The height down here at the bottom is that hit the ground, so that h2 is 0. So we put 0 in for here. This also will be gone. So what we end up having here is we have mgh1 as the height at the top equals 1/2 mv2, so velocity at the bottom, squared. Good. Okay. So what we're trying to do, you'll notice also here that we have masses on both sides. So we cancel that out, and the mass of this object doesn't even matter. So it doesn't matter what the mass of the object is, whatever jumps off this cliff, that's not even going to be important on this. So we end up with, and I'll just rearrange it, I'll put it on the other side. We have, well, I won't do it yet. We'll do we'll multiply both sides by 2, and we'll flip it, I guess. So I'm going to have v2 squared equals 2gh. Hopefully you can see that I did that. I flipped it over and then I took 2 times the other side. So v2 is the velocity at the bottom. It happens to be our impact velocity. It's how fast it's going to be going when it hits the ground. So we've come up with an equation. We can do velocity equals the square root of 2 times gravity times the height. So there we have an awesome equation for impact velocity of something that falls from rest down a certain height. And the only thing we need to know is in this equation, well, we also need to know what gravity is on the planet, but a lot of times we're assuming it's Earth, and so that's 9.81 or approximately 10. But really all we need to know is the height, and we can figure out how fast we're going at the bottom. So in this one we were going, we're dropping 80 meters. So we have the velocity would equal the square root of 2 times 9.81, but in this case I'll just put 10 to round it off to make it easy, times the height, which is 80. So 80 times 10 is 800, times 2 is 1600. So the square root of 1600 would be 40 meters per second. So all I had to know is that we're falling 80 meters, and I can take the square root of 2 times gravity times the height, and I can figure out that we're going to be traveling, we're going to impact the ground at 40 meters per second. So here's a nice equation you can put on your Herman's Helping Hand and remember for the future, because that's a good way to figure out the impact velocity. So we will QED that derivation.